This is from CSC Regular, bearing roll number 21011A0526. And today I'm going to discuss about the topic of superconductor based energy storage. Introduction to superconductors. First, let us study about superconductors. What are the superconductors? Superconductors are the materials that, when cooled below a specific temperature, that specific temperature is called critical temperature also. That in that case, superconductors exhibit zero electrical resistance and expel magnetic fields. These properties enable superconductors to conduct electricity without energy loss, making them incredibly efficient for power transmission and storage. Then the key properties of the superconductors are mentioned here as zero resistance and perfect diamagnetism. Let us discuss about zero resistance. Zero electrical resistance is nothing but these superconductors are different from the conventional conductors. Actually, conventional conductors are like copper and aluminum carries electricity and some energy is lost due to resistance, and that energy is also converted into heat. But in superconductors, this resistance disappears completely, allowing uninterrupted current flow indefinitely without energy loss. Then what about perfect diamagnetism? It is also known as Meissner effect. When a material becomes superconducting, it expels all external magnetic fields from its interior. This leads to magnetic levitation, which is widely used in applications such as maglev trains and superconducting energy storage systems. These are the key properties and the basic information about superconductors. Then let us go for the importance of energy storage. Energy storage is a critical component of modern electrical grids like industrial applications and also transportation. It helps to balance supply and demand, enhance grid stability, and store excess energy from renewable sources. We can see that energy is important due to three factors mentioned here, like for modern grids, modern power grids need stability. Electricity demand fluctuates throughout the day, and the power grids must continuously match supply with the demand. Energy storage prevents blackouts, voltage drops, and also power disruptions by ensuring continuous power supply. The existing solutions have limitations. The present existing solutions like lithium-ion batteries degrade over time and have limited charge cycles. About flywheels, they experience mechanical wear and have limited energy capacity. Pumped hydro storage requires specific geographical conditions and large infrastructure. So these existing solutions have limitations and we need a better and efficient energy storage system. Future energy demands demand advanced storage solutions. As we transition to renewable energy sources, storage systems must efficiently store and release energy whenever needed. SMES technology offers an ultra-fast, highly efficient alternative to existing storage methods. Then, superconducting magnetic energy storage, SMES. It's also known as SMES. It is an energy storage system that stores electricity as a circulating current in a superconducting coil, generating a magnetic field. Unlike batteries, which convert electrical energy into chemical energy, SMES store energy directly as an electromagnetic field, enabling rapid charge and discharge cycles. How is energy stored in SMES? When electric current flows through a superconducting coil, it creates a magnetic field that stores the energy. Since the superconductor has zero resistance, the current continues to flow indefinitely without any loss. When needed, the stored energy can be instantly extracted from the system. Then let us discuss about the key components of the SMES. Like we can see, there are the four important key components like superconducting coil, cryogenic system, power conditioning system, and also vacuum chamber. In some systems, there will be controlling systems also. So let us discuss about superconducting coil. It is made from high temperature superconducting materials such as yttrium, barium, copper oxide, or MgB2, that is magnesium diboride. It stores energy in the form of a magnetic field. Then cryogenic cooling system. Superconductors need to be cooled below their critical temperature, as we discussed earlier, because they show the property of zero resistance only when they are cooled below some certain temperature, which is also called critical temperature. And this is achieved using cryogenic cooling systems such as liquid helium or liquid nitrogen. Liquid helium, it needs minus 269 degrees Celsius and liquid nitrogen needs minus 196 degrees Celsius. Then power conditioning system manages the input and output of energy from the SMAS system. It also ensures proper voltage and frequency regulation. The vacuum chamber. It surrounds the superconducting coil to minimize heat transfer and reduce energy loss. Then how does SMAS work? There are mainly three phases like charging phase, then energy storage and discharge phase. Charging phase, electric current is supplied to the superconducting coil generating a magnetic field. In this phase, electric current is supplied to the superconducting coil so that the magnetic field is generated. The current remains circulating indefinitely without any resistance. Then energy storage. Energy is stored in the form of a magnetic field without any degradation over time. Then discharge phase. It is also known as energy release phase. In this phase, the stored energy is extracted by allowing the current to flow back into the power grid or other systems. Unlike batteries, SMAS has no chemical reaction or degradation, allowing unlimited charge or discharge cycles. Then we can compare SMAS with other storage systems, and we can see it is having every feature in the best way. Only in the case of energy density, it is low. So we can say SMAS is best suited for applications that require high power and instant response but has low energy density. We can see that it is having high efficiency than the other. Response time is also very less compared to the others, and cycle life is also unlimited. But only the minus or negative thing is that it is having the low energy density. So that's why it is used for the applications that require high power and instant response. Then advantages of SMAS. Ultra fast response time. SMAS can release energy in milliseconds, making it ideal for power grid stabilization. It is also having high efficiency as there is no electrical resistance and almost no energy is lost. Unlimited cycle life, that is also known as unlimited charge or discharge cycles. Unlike batteries, SMAS does not degrade and can be used indefinitely. It is also environmentally friendly, and it is also having the grid stability that it provides instantaneous energy release for grid stability. Then challenges in SMAS, high cost. Cryogenic systems and superconducting materials are expensive, so that it costs a lot for any organizations to implement the SMAS storage systems. And low energy density. SMAS is better suited for high power short duration applications like grid stabilization rather than long-term energy storage. Compared to lithium-ion batteries, which store large amounts of energy in chemical form, SMAS stores energy as a magnetic field, which has only limited capacity. Then cooling requirements. The system needs to be continuously cooled to keep the superconductors in their zero resistance state. This requires advanced refrigeration technology, which consumes additional power compared to the basic or normal conditions. Material limitations. Superconducting materials like yttrium, barium, YBCO or BSCCO and MgB2 are expensive and have limitations. Then SMAS in renewable energy. Why is actually energy storage crucial for renewable? Solar and wind power are intermittent, meaning they do not generate energy consistently. So SMAS can help store excess energy when production is high and release it instantly when needed. So how does SMAS supports renewable energy? You can see here, it balances the fluctuations in wind and solar power. How can it be balanced? Let us see that. Wind speeds change frequently and solar power is only available during daylight. So SMAS provides a way to stabilize the power supply by instantly compensating these fluctuations. It also provides grid stability. What do you mean by that? When solar or wind power suddenly drops, SMAS can inject stored energy into the grid within milliseconds. It also prevents power blackouts and voltage instability. Then the other thing is instantaneous backups. It enables instantaneous backup power. Unlike batteries, which have a lag in response time, SMAS can immediately discharge storage energy. Useful for critical applications like hospitals and data centers. Then SMEs in transportation. SMS nowadays SMA is also used in transportation. Like for example, high-speed rail and maglev trains. Superconducting maglev trains are using superconducting magnets to levitate and reduce friction. SMEs provides bursts of energy to accelerate trains quickly. The example for these type of applications in transportations are Japan's SC maglev train, which uses superconducting technology for speeds over 600 km/h. Then the next application or in transportation is energy burst for acceleration. Trains and electric vehicles require large amounts of energy to start moving. So these SMEs can provide instantaneous high power bursts, improving efficiency of the vehicle. Then braking energy recovery. When a train slowdowns or stops, kinetic energy is usually lost as heat, as we know. But these SMEs stores this braking energy and reuses it for the next acceleration phase, so that the energy waste is reduced. These are the applications of SMEs in transportation. Let us see the uses of SMEs in industrial as well as military in the military field. Like in the industrial applications are, for first one is backup power for factories and data centers. It is also used for power quality enhancement. In the military applications, it can be used for electromagnetic railguns, directed energy weapons. These are the different applications of SMEs in industrial as well as military uses. Then real world implementations of SMEs. SMEs is already being tested and deployed in various countries. Like in Japan, it is used in the power grids for voltage stabilization and industrial energy management. The example for this is Chubu Electric Power Grids SMEs project. In USA, the Department of Energy is investing in high power SMEs research. MIT and also national labs are working on making SMEs more affordable. Then Germany. The companies uses SMEs for industrial power backup, ensuring smooth factory operations without power losses. Then let us discuss about the advances in superconducting materials. High temperature superconductors. Traditional superconductors require very low temperatures. HTS materials like YBCOR can operate at high temperature, like for example 90 Kelvin or minus 183 degrees Celsius, reducing cooling costs. There is also advancement like new materials enhancing feasibility. Magnesium diboride is an affordable superconductor with promising properties. Then the next advancement is nano-engineered superconductors. Scientists are developing nano-layered superconductors to improve magnetic field strength and efficiency. Then future of SMEs. The future of SMEs includes lowering costs with advanced materials, like using cheaper or more efficient superconductors. This can reduce cooling requirements through better insulation. Then the next is hybrid storage systems, like we can use SMEs along with the batteries for the better efficiency. Then we can also use better cooling technologies which reduce energy consumption. Then ongoing research and development. As we have discussed that MIT and DOE are researching on this SMEs for better efficiency and affordable materials which can be used for the reduced energy wastage in the storage systems. And also some private companies are investing in these SMEs storage systems to build a better and efficient systems. And also AI is integrated with this SMEs so that it can help in smart grid optimization. Then conclusion. We can conclude that SMEs is highly efficient and it can provide rapid response energy storage solution. So, and also has many applications in the different fields like industrial, military, and also in the other applications, so that it can be used widely. But the only thing is it has a low energy density compared to the other systems. And there are also some ongoing advancements which makes SMEs is as the best one in the among the energy storage systems. Thank you.